Now that we've seen some of the criteria, let's actually look at how to implement them in practice. And we're going to follow the life cycle again, where the first step will be pre-processing. So this is the point now where we already have data collected, and now we want to see whether we can modify and transform that data using some of the fairness criteria that we've seen in the previous section. So what are pre-processing methods? Well, collection of methods that modify the data or the labels before the model is trained, and again with the goal to mitigate bias. And there's a whole list of different methods or techniques that we could try. First one that you see listed here is the so-called suppression technique. What does suppression do? Well, suppression refers to deleting all sensitive features or all sensitive columns that you have in your dataset. And careful with this, because there could actually be proxies present in your dataset. So we'll have a look at that in just a moment. The second technique that you see here is the so-called re-weighting, where we want to make the group membership and outcome independent. So we're going to apply weights to individual data points according to the probabilities that we've seen introduced in an earlier section. And finally, we could actually go and transform the data altogether by generating synthetic features or even labels. And once again, ... because as I mentioned, there are many more techniques out there. And they will depend on what kind of model we're trying to build, what kind of problem we're trying to solve. The first example that we had was suppression. If you just remove all the sensitive attributes from your dataset, well, then the model will have no chance of picking up on those. But unfortunately, it was found to be rather ineffective due to the existence of proxies. And nowadays we have very rich data sources, so the chances that there is a proxy that is highly correlated with one of the sensitive features is indeed very high. Another caveat or another issue is that if you delete the features, that actually makes it impossible to disentangle the effects downstream. And as a final note here, there might actually be a legal requirement to deleting those features. We had a look at disparate impact and disparate treatment earlier on, and it might be the case that in certain industries you actually do need to follow this suppression principle and simply not use those features, which would be equivalent to saying that you're deleting them or dropping them from your dataset. And a historical example of things gone wrong where this proxy issue did actually occur is shown on the right-hand side here, the redlining in the banking industry. So as we know that there is a law that forbids to use race as a feature when it comes to deciding on whether or not loans are approved or denied. ZIP code, however, was not protected by the law. So what happened was that different institutes actually used the ZIP code as a proxy, and then you have these so-called redlining districts. Let's have a look at re-weighting then. So here the idea is that if two events are independent, well, then we can multiply the probability of the attribute value occurring with the probability of a certain outcome occurring. So keep in mind here again that we have a certain outcome, positive or negative, and we also have an indicator that states whether or not we are member of a group. So the A here refers to group membership, and this could be composed of many different attributes. And then we have the Y here that denotes the outcome. And if those two are truly independent, and this follows from some basic probabilities, well, then we can take the individual probabilities, so the probability of belonging to a certain group, times the probability of having a certain outcome. If we now rearrange the equation, we get a weighting factor, and this weighting factor is now going to be the probability of belonging to a group times the probability of having a certain outcome divided by the probability of having a certain outcome and belonging to a certain group. And we'll see this calculated in the next slide. So here's our example, and we will need to calculate all the possible permutations of attributes and outcomes. This example here is taken directly from the Caldas et al. Paper, where the sensitive attribute that they considered, which was also measured as binary male and female, was the sex. and then we have the outcome from a classifier as either positive or negative. And then how do we calculate the weighting factor? Well, first we need to look at what is the probability in a small data set to be female. The probability here, there are 10 data points in total, 5 of which are female. So probability in this data set to be female is 5/10 times the probability of having a certain outcome. For now, we're interested in the positive outcome. And we see that there are 6 positive outcomes in this data set. So 6/10 is the probability of having a positive outcome. And now we need to divide through the probability of being female and having a positive outcome. So once again, how many cases does that apply to? Well, there's only 2 females with positive outcomes, 10 data points in total, so 2/10. So what we get then is a weighting factor of 1.5 for female positive. And now we need to repeat this for female negative, male positive, and male negative. And as a result, we get the weighting factors that are in the furthermost right column in the dataset. So now that we have these weights, what can we actually do with them? Well, first of all, we could plug them in directly into certain algorithms. So certain algorithms will directly consume different weights for different data points. And one particular example is shown here. That is the logistic regression, where we can actually specify during the fit or during the training of the model what kind of weight we want to use for the individual data points. So really what this is it's equivalent to an upsampling or downsampling of different data points, but instead of creating copies of data points, which might be computationally inefficient or take up too much storage, we're just using the weights directly. The final pre-processing method that we want to look at is the so-called disparate impact remover, and it's actually going back to the independence or separation criteria once again, where we said we can rearrange these probability values and form a ratio, and that gives us the so-called disparate impact metric. So what we have here on the right-hand side is once again a classification example with 2 features, age and income, and you see denoted as plus or positive all the approved outcomes, and minus or negative are the denied outcomes. And we've now also overlaid 2 different groups. There's one group that is favored and then the other group that is disfavored. And we could actually quantify which group is favored and disfavored by looking at the rates of positive outcomes and comparing them using some of the pre-training measures that we already encountered in an earlier section. So how can we use this DI metric now to transform our data? First of all, let's calculate the success with the favored attribute value. So the probability of success here is 10/16. The success with the unfavored attribute value is 5/20. And if we now use these values and plug them into our calculation, well, then we get a disparate impact of 0.4. And I already mentioned that this is actually one of the metrics that has found its way into legal literature, where we have the 4/5 rule, or we can also say that there is adverse impact that we need to mitigate if the DI value is less than or equal to 0.8, which in our case it is. So we do actually need to perform a transformation. So how can we actually remove the DI? So a classifier is considered free of disparate impact if the value of the sensitive attribute cannot be predicted from X, the remaining features. So now we're going to denote some of our features as these special sensitive attribute features, and we're going to transform or shift the remaining features, the X, with respect to what we observe in A. So first of all, we need to set a threshold of how much we want to transform our data, and then we need to find a method to actually adjust the distributions of X such that A cannot be predicted at the epsilon threshold. And there are, again, different methods in which we could achieve that, and you see a couple of them listed here. We're going to have a quick look at an example now on how this would work in practice. First of all, we have our data set here from SAT scores, with, once again, the example here is going to be a binary gender split. We have a score and then an admissions outcome as either positive or negative. So this is a classification example. We have one sensitive attribute here, which is going to be the gender column, and then we have a score. And the idea now is to transform the score value. How can we achieve that? Well, first of all, we need to split our groups based on the sensitive attribute value. And then we'll need to order the scores within those groups as well. Secondly, we then need to split these subgroups that we've just formed based on the positive and negative outcomes. And then finally, we need to replace the feature value of the disfavored group with the median feature value of the favored outcome subgroup. Sounds a bit obscure, so let's have a look at it on the next slide, step by step. So first we have our data set, and we split it between female and male. So there's 2 entries for female and 4 for male. Secondly, we need to sort by scores. So you can see here in the male subgroup, we're actually rearranging a data point to bring up the 1400 SAT score to the top. And final step now is going to be, we need to compute the median value per outcome. So we have positive and negative outcomes. The median outcome for admission denied is 1400, and the median outcome for admission approved or accepted is 1500. And what we're going to do with these scores now is we're going to replace the female score with the male median. So that is going to shift our distribution of the female dataset to bring it closer to the male, or in this example, favored group. The previous slide was a quite artificial example with only very few data points, but if we were to simulate this on a wider range and hypothetical range of SAT scores, we can see here on the left-hand side the original male curve, and then the right-hand side in blue the female curve, and then in the center we get repaired female. How would we achieve this in practice? Well, in practice we would use SMODE to generate synthetic data for the underrepresented individuals to increase the prevalence of those data points. To wrap up on the pre-processing methods, let's briefly discuss some of the limitations. So we already know that there are trade-offs between the primary objective and the fairness improvement, the mitigation of bias that we want to achieve. And more specifically, some of the issues that we have with the methods that I introduced on the earlier slides is that in the suppression technique that I showed you, once the information is removed, we cannot re-engineer it back. So it might actually be better to keep the data as is and not perform any transformation or delete any features, because then we can investigate later on in the life cycle as well. Also, we cannot be sure that we've actually captured all proxies, so even if we run correlation tests and we hope that we've identified all of the features that are correlated with the sensitive attributes, we cannot be certain because there could be a more hidden relationship. So it might make sense to keep all the information and then use it later on. And finally, if we also perform transformations, well then these new and transformed distributions, this synthetic data, they can actually be rather far from the natural distributions. So again, this might be complicating things when it actually comes to making model predictions, because we may not observe such a transformed value in reality. And we already called out that there are these laziness issues where we could say that we want to accept the top 50% of the favored group and random 50% of the unfavored group, and that would mean meeting the criteria, but obviously that is not a desired solution or desired outcome. To wrap up the conversation about DI and data transformation, we're going to have a look at a notebook here where we're going to first of all measure DI and then also perform the transformation. So in this notebook, we can see how to quantify disparate impact. We're going to calculate the measure up front. We'll then implement a disparate impact remover, and then we'll quantify again. And as a model here, we're going to use logistic regression, and we're going to build a classifier.